Okay, so Peng Yan, I'm very sorry that I cannot come to the conference in person. So I also thank the organizers to give me this opportunity to introduce our recent work on Magnon frequency code. This is my title. So the content of my talk today is based on two papers we recently finished. So most of the calculations was done by my postdoc, Dr. Dr. Zheng Wang, and with assistant from Zhishong Li and Yunshan Chao from the same institute, and also with kind help from Dr. Huayuan Yang and Rambert from University of Utrecht in Netherlands. Okay, here, this is the outline of my talk. First of all, I will give a very brief introduction to the concept of frequency cube, and then I will introduce one of the main results of my talk is the Magnon frequency cube. So we call it MFC. So to generate the Magnon frequency cube, we need a very strong 3 Magnon processes. So I will give an introduction to 3 and 4 Magnon processes in magnetic textures. And I will also introduce the mode conference and the stimulated splitting, which is very helpful to understand the creation of Magnon frequency code. Furthermore, so if we put the frequency code in a magnetic nano disk, which has rotational symmetry, then the Magnon will carry finite orbital angular momentum. So in this case, we call it twisted Magnon frequency code. I will to introduce this result, I will discuss the Magnon vortex scattering. So this is a nonlinear scattering, and I will also show our result about the selection rule in the nonlinear Magnon vortex scattering. And finally, I will give an interesting analog of Magnon to the Penrose sulfur radiance processes. In the end, it's my summary of my talk. So I think here in the left corner of my slide, this is a very common device, so which everyone use it every day. This is called code. I think the two most obvious characteristics of comb is that it is discrete and equally spaced. So these two properties is built on real space. That means that the equally spaced is measured in spaces. However, if we change the space, the real space to frequency space, so the basic unit is not centimeter or millimeter, but hertz, then the comb will become a frequency cube. The frequency cube also have these two interesting properties that are discrete and equal spaces, but which is in frequency space. Because of this interesting property, so we can use a frequency cube to measure the spectrum of very complex samples. For example, if we have a frequency cube structure here in the left, if we input the cube through a sample and measure the output spectrum. So if we do the experiment and find some peaks enhanced or narrowed, so we can say that this sample must have this kind of spectrum. So this is can be used for spectrometer. So because of this property of frequency cube, the Nobel Prize in 2005 was given to these 3 gentlemen. So including because of the great contributions to quantum theory of optical coherence, which of course include the optical frequency scope technique. So actually, there are many applications of optical frequency scope. For example, it can be used for optical clocks, and it can be used to search dark matters, and even for disease diagnosis. Because of the great success of the optical frequency scope, now it inspires people to look for other solutions in different systems. For example, people working in photonics also propose that the 3 Follow processes can be used to generate the photonic frequency scope. So this theoretical proposal appears in 2014, and 3 years later it was confirmed by experiments. So because photon follow and Magnon, both so all of these quasi particles are bosonic. They should share very similar properties. So in this sense, we can say that also, okay, the optical frequency scope and the photonic frequency scope has already been studied extensively, but the magnetic frequency scope is rarely studied because the very weak nonlinearity in uniform ferromagnetic states. So this because the nonlinearity effect is weak. Particularly for the 3 Magnon process. So this is usually it is regarded very weak. So in order to see how the nonlinear Magnon-Magnon interaction arises in magnetic system, we can start a very general Hamiltonian, so, which can be include the exchange, anisotropy, exchange Maria, and even the dipole-dipole interaction. So if we consider background ground states, so which can be either uniform or non-uniform. So it doesn't matter. So if we start with the ground states, so we can do some small perturbations, and by the Hostin-Primarkov transformation, so we can expand the Hamiltonian into a Taylor expansion. So we have we observed that there are many terms. So from starting from lowest ground state energy to linear spin waves term, and the 3 Magnon interaction and the 4 Magnon term. So in terms of Taylor expansion, so people usually say that the 3 Magnon process should be stronger than the 4 Magnon processes, but in magnetic system is not the case, because the 3 Magnon process, 3 Magnon term usually comes from the very weak dipole-dipole interaction, but the strong 4 Magnon processes comes from the very strong the exchange interaction. So in some sense, the 4 Magnon processes is stronger than the 3 Magnon processes. However, if we want to generate the Magnon frequency scope, we need 3 Magnon processes especially in two dimensions. So this, first of all, I will give a so-called no-go theory. So one can prove that in two-dimensional or higher dimensional cases, the 4 Magnon process cannot generate the curve structure, the discrete curve structure, because based on very simple conservation laws, which are energy conservation and the momentum conservation, we consider very simple dispersion relation. We can prove that in two dimensions, the 4 Magnon process can generate continuous spectrum. So this this shows that if we have two mode, and if we have 4 Magnon processes which will generate omega-3 and omega-4. So based on these two conservation laws, it can generate continuous spectrums which is not discrete. So this is called a no-go theorem, that in 2 and higher dimensions, the 4 Magnon process cannot generate a discrete curve structure. But this does not include the 1 dimension. For 1 dimension, the 4 Magnon process indeed can generate curve structure, but this is what we discussed today. So the situation is that we want very strong 3 Magnon processes instead of 4 Magnon processes, but usually in uniform ferromagnetic, the 3 Magnon processor is weak, much weaker than the 4 Magnon processes. So this seems like a dilemma. So how can we solve it? So this is this table. This table summarizes the mechanics for 3 Magnon processes. In uniform ferromagnets, both the dipole-dipole interaction and the Jarzinski-Moreira interaction can generate the 3 Magnon interaction term. As we know, as I mentioned before, so these two interactions usually is much weaker than the exchange interaction. But the exchange interaction cannot generate 3 Magnon term. It can. The lowest nonlinear term is 4 Magnon interaction, which is not what we want. However, recently we find that if the ferromagnetic state is not uniform, but it has some spin textures, so this is we find that the magnetic textures, even without dipole-dipole interaction, can significantly enhance the nonlinear 3 Magnon processes. So, for example, we have studied the scormion, domain and the vortex. So in all these systems, the magnetic ground state is non-uniform. So we find that in these magnetic textures, the large magnetization gradient can significantly enhances the nonlinearity, the 3 Magnon processes. So this is indeed what we want. So in 3 Magnon process, there are two basic processes which include the confluence and the splitting. So the confluence, so from its name, we can see that there are two input and give output. This is for confluence, but we also have a splitting, which is the 1 Magnon is split into 2 modes. So if we can, but we can divide the splitting into 2 cases. So in this case, so we have one mode. It simultaneously or spontaneously split. So we call it spontaneous splitting. But if we have a extra mode KB, so the splitting will be projected to KB mode and K2 mode. So because of the presence of KB mode, so the splitting is stimulated. So we call it stimulated splitting. So this concept was first proposed in our work 4 years ago. And the stimulated Magnon splitting was also confirmed by experiments 1 year later. So this is the basic introduction. So in order to find the magnetic frequency code structure, Magnon code structure, so we study the nonlinear interaction between spin waves and the magnetic vortex. So we consider a magnetic null disk here. So the cyclic is D and the radius is R. So in this VC, we use VC to represent the vortex core. So this VC is vortex core. It can gyrate around the geometry center. However, if we have a twisted spin wave mode here, so their nonlinear interaction will generate a frequency code. So this omega L is the frequency of twisted spin wave, the eigenmode of the spin wave in the narrow disk, and the distance between the code is omega G, which is equal to the gyration frequency of the vortex core. And this is the energy, the selection rule for the energy conservation. However, because of the rotational symmetry, this system also this system also allows angular momentum conservation. So this is another selection rule. Because of this selection rule, so each spectrum line carries different orbital angular momentum. So this, for example, if we have this is 0, the angular momentum, orbital angular momentum is 0, and the other mode can be 1, 2. So this can be an arbitrary integral. So this is the concept or the picture to generate the Magnon frequency code. in order to simulate, we can see it indeed happens. So in this system, we first simulated the spectrum of the magnetic vortex. So this is the vortex core. So we could do this Fourier transformation of the excitation spectrum. We can find that there is very low frequency peak, which represents the gyration, gyrotropic mode of the VC, the vortex core. And there are other two non-degenerate twisted spin wave, which the no one represented the clockwise rotation, and the other one represents the anti or the counterclockwise rotation. These two modes is not degenerated because of the magnetostatic coupling, so which splits these two modes. So if we, in this case, so if we want to generate or excite the twisted the frequency curve, we input. So we use a high frequency mode. So we use this mode to generate, to excite, to drive the nano disk. So we can see that if we increase the amplitude of microwave field, we can see that there are many frequency branches with particularly in this region, we can observe very clear comb structure, which distance, with equal distance, and the distance is exactly the frequency of the vortex core gyration. And we can, this is the frequency information. However, if we look at the orbital angular momentum, we can see that this different spectral line carries different orbital angular momentum quantum number. So from -2 to 3. So we have at least here we observed 6 spectral lines in the comb structure of magnons. So if we look at the distribution of wave function, we can see that it indeed carries different orbital angular momentum. So this is the input mode. This is this mode is our input, which is have a very high frequency. It's about 6.74 gigahertz, which is much larger than the vortex gyration frequency omega g. This omega g is only 0.18 gigahertz. So this is a purely a nonlinear effect. So we use this high frequency to drive the large disks, and we observe a very rich spectrum. For example, we can observe the vortex gyration and the vortex gyration frequency doubling and tripling, and we also observe the confluence and the splitting. So this simulation result confirms the selection rule, which requires both the conservation of energy and the orbital angular momentum. So this is the first result of the selection rule. In previous simulations, we did not include the thermal effect, so which means that we did everything in zero temperature. But how about we heat it? So in this case, we find that the spectrum, the wave function, there have some random information and random phenomenon. However, the strength of the peak is significantly enhanced. So initially we find it it is very surprising, because usually the thermal effect is not good for any physics, interest physics. But in here, the heating effect is constructively to enhance, to improve the signal. So we find that the reason is that at the finite temperature, even the low frequency vortex gyration is excited by the thermal fluctuations. So we do not need, initially we have this KB mode. So from this this result, we can find that if for the zero temperature, the vortex gyration is initially is absent, because we shine the lattice with a very high frequency mode, the omega L. So but in the presence of the thermal fluctuations, even the vortex gyration is generated due to the thermal fluctuations. Yeah. Okay, let's look at the spectral line number again. So in previous result, we find that the spectral line has only 6 spectral lines. So this is because of the selection rule, because the red dots represent the comb structure, and these blank symbols represent the spectrum of the spin wave spectrum in the Lardo disk. We find that only the overlap region there will be a frequency comb structure. Outside this region, because the frequency mismatch, so the frequency comb cannot stably exist inside the Lardo disk. However, this small number of spectral line can be improved by increase the size of the Lardo disk. For example, if we use a bigger Lardo disk with a larger gradient radius, so the spectral line will increase linearly. So we have find that if we increase the radius from 100 nanometer to 500 nanometers, the spectral line of the frequency comb is almost doubles. So it was almost follows a linear relation. However, the problem is that in the two sides of the frequency comb, the strength of the comb is significantly suppressed. So the problem is that how to amplify the twisted magnon. So for example, only the central peak is very strong, but it gradually decreases. However, if we want to use very useful magnon frequency comb, we do not want to see the decay of the strength of the comb peak, but how can we amplify it? So we get some indication from the Roger Penrose. So he proposed in this process in 1969, and when he studied the rotating black hole. So in his pioneer work, he proposed that we can extract energy from a rotating black hole. So this picture was generalized by Zeldovich in 2 years later. He studied amplified of electromagnetic wave shine on a rotating metallic cylinder. So when this condition is satisfied, the electromagnetic wave can be significantly enhanced. So this is some animation. Okay, so in our system, so we have twisted magnons, which is play the role of electromagnetic wave. We also have a gyrating vortex core, so which play the role of rotating black hole or rotating metallic cylinder. So because of this mapping, so if we want to see the Magnon Penrose superradiance or the Magnon Zeldovich criteria, so we must have this condition to be met. This omega L is the frequency of the twisted magnon. This L is the optical angular momentum of the magnon, and omega G is the frequency of the vortex. So how to meet this satisfy this condition? So we did many simulations and studies, and finally we find that if we consider very thick narrow disk, for example, if the narrow disk thick is larger than 20 nanometers, and also we need a perpendicular magnetic field. So in this blue region, so we can say that this Magnon Zeldovich criteria can be met in this region. So because of the presence of the perpendicular magnetic field, so the UEL magnetic vortex is not in plane polarized, but it's have a cone-like vortex. It's a vortex cone or something, or cone vortex. So in this case, we find that we have found that if the condition is met, we find a very interesting phenomenon that the spectrum indeed is significantly enhanced. So this blue part represents the enhancement, the amplified. So we also find the very interesting trapping effect. So so for the if the super-Lorentz condition is met, so the low frequency part is trapped within the quartz gyration core, and the higher order mode is amplified and is expelled outside of the vortex gyration. So this because of this phenomenon, we can see that the vortex gyration orbits acts as the ergo regime of rotation black hole. So this is our observation and exploration. So this is the summary. So we have studied the condensation effect of Magnon fluoroscope, and we also predict Magnon parent super-radiancy effects, and our results suggest a promising way to generate twisted Magnon with very high orbital angular momentum and to improve the flatness of the Magnon core. And also, our result also need a pathway to simulating the rotating black holes in magnetic platform. So some details can be found in our two recent work. Thank you very much.
Thank you. Now the